transverse layers. We're also currently certified on Doug fir larch as well, so we could offer different species to different clients based on different aesthetic and structural needs. All of our raw materials come from the green storage building onto our decoupled sorting line here. This is where we do our scanning, sawing, and sorting of the materials. As you can see to my right here, everything is coming off of the tilt hoist. It's going to go through a scanner, then it's going to be cut if needed, and then be sorted into one of 30 different bins. Different things that we scan for are bow, crook, warp, twist, any knot sizes, different variations, and it goes into one of the 30 different bins based on aesthetic, moisture, and other structural properties of the board. One of the things that we sort for on the decoupled sorting line is the moisture content of the board. We can't accept anything greater than a 15% moisture content in the process. Therefore, anything 15% or greater needs to be dried down. What we use for drying is a continuous dry kiln, 13 million BTUs. As you'll see here behind me, each unit is stickered, which allows for airflow to pass through the unit for even and effective drying of the unit. Now that we've sorted the boards out of where we want to have them within each panel, we have the short boards on top, which make up the width of the panel, either 10 or 12 feet, and the long boards, which gets finger jointed together, which make up the length of the panel at 60 feet long. After our long boards and short boards are separated, the long boards come here to the finger joiner, and this is so we could create the 60-foot length for the length of our panel. What we're doing here is we're cutting fingers into the boards, which then have glue applied to them, end up getting jammed together, then going through an RF tunnel for an almost instant cure. After the finger joining process, we need to cut the long boards down into those 60-foot lengths. This is achieved by the flying saw, which moves in line with the board and cuts at exactly 60 feet 6 inches. After the flying saw performs its task, the boards go through planer number 3, get planed down to the net size, and come to this long board storage system. Each one of these trays here effectively represents each layer of the longitudinal part of the panel right before it goes to the pressing and layup. After the long boards and the short boards get separated and the manufacturing operations are completed on those, they come together here at the pressing and application station. What we do is we have the gantry with the long boards comes down, the glue applicator runs across it, the gantry with the short boards comes down, the glue applicator comes back, and you keep going until you hit 3, 5, 7, or 9 layers. After the layup is complete, then it's into the press for pressing. Now that we've finished the layup process, we've rolled our billets here into the press. We're going to press down from 3 different axes. We're going to have top down, we're going to have our side squeeze, and we're going to have our end squeeze. The reason that we push from 3 different axes is to ensure that we have a really tight panel, which is better for fire performance, structural performance, and gives a better end look to the customer. This panel here is hot off the press. It is 60 feet long, 12 feet wide. This one right here is a 5-ply at 6.9 inches tall. We're about to go into the CNC machine to get all cleaned up and cut into the finished panel sizes. So this is a 9-ply panel here. This is the thickest panel we make at little over a foot tall. This one's a Douglas fir here, as you could tell. It has a little bit of a reddish tint compared to the spruce pine fir. And this was one that we actually completed for one of our certification efforts recently here. One of the largest panels you'll ever see. This is one of our 3 CNC machines here. The CNC machines have 3 primary functions: to square off the panel after it comes out of the press, to put the spline or any type of rebate connection into the panel, which is used for the panel-to-panel connections in the field. And then the last thing it does is cuts any MEP penetrations into the panel that may be required. And this is the final step before it goes off to the sander. If you've ever used a belt sander before, this is our idea of one. This is the last step of the manufacturing process, which is the sander. This happens right after the CNC machine. What we do is we take about 1 millimeter off the top and the bottom, and this allows for a nice, smooth, uniform finish across the whole panel. Right after this, what we do is we put on an end grain sealer, which protects the panel from logistics to construction. The environmental conditions of CLT manufacturing are critically important. That's why we monitor the temperature and humidity very closely. The temperature range needs to be 70 degrees plus or minus 5, and we're between 45 and 55% humidity. Due to the different seasons of the year and the humidity here in Spokane, we have to add in humidity at certain times to keep ourselves in between that 45 and 55% range. This allows for optimum adhesion of the gluing and application process. With all the scanning and sorting we do, we capture all the unique attributes of the board by this unique identifier here, which is a QR code. This QR code is placed on every single board and it's tracked throughout the manufacturing process. We track all the attributes of the board as they go through the manufacturing operations all the way to the finished panel.
All right, thanks, Damon. And now I think we're going to move over to the catalyst building.
Hi, I'm Cora Todd, Project Manager for Katerra Construction, and this is the South Landing Catalyst Building. And I'm excited to take you for a tour. Let's go take a look. In the Catalyst Building at South Landing, it's 160,000 square feet of Type 4 heavy timber construction. We use glulam beams out of Canada, and we use 3 different sizes of CLT in this structure. The 7-ply shear walls are by Structurlam. The 3-ply exterior walls are also by Structurlam, and the 5-ply floor panels, both in flat panel and built-up double T panels, are from right here in the Spokane Valley out of our Katerra CLT factory. It aims to be one of the largest zero energy and zero carbon buildings in North America and will pursue zero energy certification by the International Living Future Institute. The 5-story office building is a result of a cross-industry team of partners, including utility provider Avista, design-build engineering firm McKinstry, and Katerra. Working with Katerra design partner Michael Green Architecture as the design architect, Katerra is the architect of record and general contractor for the building. The building makes extensive use of CLT in design and structural elements, including floors, shear walls, and building envelope, which enables near passive house levels of thermal performance. So let's start by looking at the 7-ply panels from Structurlam. 7-ply shear wall elements erected in 2 lifts using a spliced epoxied rod system allowed for ease of erection and constructability. We were able to gain quite a bit of schedule using this system, even having to do a half-lap joint in the middle to span the lengths that we needed. And you can see here, this is where these 2 panels splice together and the screws tie them to each other. Katerra needed to use 7- and 3-ply panels from Structurlam because at the start of construction and when we needed to start producing materials, Katerra was only certified to produce 5-ply panels. We have since then received our certification to produce 3-ply panels and are currently in process for getting certification for both 7- and 9-ply panels. 10 by 30 3-ply exterior wall panels from Structurlam are built up of 3-ply CLT, rigid insulation sandwiched in metal panel, plus a rain screen system that has terracotta panels on the very outside. This was important, according to our acoustics engineer, in order to minimize the sound transmission of the active railway to the north of this site. The 3-ply panels came to us with window cutouts already present. We then installed punched window openings, which are triple pane units from Euroline windows in Canada, and the exterior envelope has an R40 average because of the minimal thermal bridging as a result of the CLT. The use of CLT in exterior walls of Type 4 heavy timber buildings is allowed. Katerra worked diligently with our code consultant and the City of Spokane to ensure all fire life safety measures were addressed with regard to flame spread. The floor-lined fire stop assembly is typical as found in aluminum curtain wall to concrete deck building. What we can still see, because TI renovations have not begun on this floor, is the gravity connection steel plate connecting the CLT3 ply to the perimeter glulam beam beneath this gypcrete. The primary tenant for the building is Eastern Washington University. They occupy approximately 60% of the building. EWU is relocating some of their technical programs to this building, including computer science and electrical engineering, ideal programs to be located in this type of structure. The grid was set up on a 30 by 30 spacing, which while not completely efficient for CLT, we were able to manage well by using ribbed panels, essentially a double T made from wood fiber instead of concrete. To our knowledge, this is the first application of this technology in the US. The Catalyst building utilizes the very first product off our factory floor. Not a single panel was sent back. We are 100% on quality for our first project. Every piece of wood that you see in here is an SPF or a spruce pine fir mixture. We upsized the glulam beam in the center bays to allow for flat panels instead of the built-up double Ts. Upsizing the center beam allowed for running of mechanical systems through these center bays and then out into the outer bays via the castellated beams that you see here. Low air leakage equates to very high performance. It's the metric that tells you how the building will perform and whether it reaches the very minimal energy allowance of a passive house building. Passive house needs to have uncontrolled leakage through gaps less than 0.6 of the total house volume per hour during a pressure test at 50 Pascal, both pressurized and depressurized. The Catalyst building measured an air leakage rate of 0.035 CFM per square foot, which is significantly below the code requirement. The results demonstrate the great workmanship and management by the Katerra construction team and rigorous detailing by the design team. Air tightness is difficult to achieve in a building of this size. Air tightness tests were done by RDH, one of the leading envelope design firms in North America. They have done over 100 similar tests, and the Catalyst building performed better than any building they have ever tested. Integrated wood slat system from Okalux was important also to achieve the passive house rating. You can see demonstrated that while I have sun coming through my punched window openings, we don't have sun coming through this very large curtain wall space. On top of our CLT panels, the floors have a 3/4 inch Acoustomat and 2 1/4 of gypcrete on top of that. This was done in order to minimize vibration from pedestrians and people walking through the structure. Panel to panel spacing, behind this piece of trim, we still have about a 2.5 inch gap, which allows for interstory movement of up to 3/4 of an inch per panel. So if in case of an earthquake, these panels would shift independently and not conflict with each other. One of the structural elements in this building is called a BRB, a buckling restrained brace. There are 22 of these at our shear course. These are concrete-filled steel tubes that have steel plates running through and basically act as a stabilizing tool that if this building were to start rocking in an earthquake, they take the forces from the diaphragm above and drive them into the very large concrete pads that we have underneath this stair core, and that happens at all 3 of our stair cores and at the knife walls in between throughout the structure. We added an extra beam at the center bay to eliminate rib panels within the center zones to allow for main distribution around the core above the corridor, then feeding branch ductwork through cutouts in the main glulam girders. The CLT within the core is an efficient span of 15 feet. The omitted beams allows utilities like ductwork to be installed tighter to the underside of the CLT. An environmentally conscious choice in this structure included capturing waste that could have gone through the chipper and utilizing it for other parts and pieces in our building. This included getting the window cutouts that came from our 3-ply panels and utilizing them for my stair treads and risers and landings in these stair cores. The finished surface in this area is going to be a rubber tread and riser, but then the underside of the CLT is all going to stay exposed. This is an example of part of the tenant build-out that Eastern Washington University has done in the Catalyst building. This is a VDC classroom, and it showcases the cloud system by Overcast Innovations and installed by McKinstry. The goal was to maintain open space while distributing electrical, mechanical, and fire alarm systems throughout the space. Commercial buildings are not required by code to provide for perimeter power. Katerra Design worked closely with McKinstry to develop strategies for routing conduit across the ceiling, through perimeter beams, and down the exterior wall in discrete locations when necessitated by future tenant fit-outs. Most office systems and layouts are serviced by floor boxes or through adjacent framed walls, which omits the need for such perimeter power and data. In this main lobby between East Tower and West Tower, Katerra and Michael Green Architecture really wanted to emphasize vertical wood elements as well as CLT panels that extend past the perimeter of the building via our cantilevered awnings. While the majority of this building is made out of wood, in this 2-story lobby, we did have to use steel elements. That steel, because it's exposed, needed to also have an intumescent coating applied before we put the finished paint on it. Now, the floor panels of level 3 create this lobby space, and Katerra thin 3-ply panels are then used as a veneer to expand between rib beams. When we put 3-ply panels from beam to beam, we created a concealed space. And because of that, Katerra had to use a fire-resistant coating because that area is not sprinkled. Katerra commissioned the Carbon Leadership Forum and Center for International Trade and Forest Products at the University of Washington to analyze the environmental impacts of RCLT as well as the Catalyst building in Spokane. These two organizations are the preeminent leaders in their respective fields. CLF recently released an embodied carbon calculator for the construction industry, and Sintrafor is well known for its research to support sustainable forestry and forest products trade. Our goal in pursuing this analysis was twofold: to better identify opportunities to reduce environmental impacts in our supply chain and improve CLT production efficiencies, and to eliminate the life cycle environmental impacts of mass timber at the whole building scale, identifying opportunities to optimize the environmental performance of mid-rise mass timber structures. The Carbon Leadership Forum found that mass timber nearly offsets all upfront embodied carbon in the Catalyst building. The life cycle assessment of the Catalyst building structure and envelope estimated the upfront embodied carbon of the building to be only 207 kilograms of carbon emission per square meter. Considering the Catalyst building stores approximately 204 kilograms of carbon per square meter of biogenic carbon, the CLT and glulam elements offset its upfront embodied carbon. While the study did not make direct comparison of the Catalyst building to similarly sized buildings constructed out of steel or concrete, its upfront embodied carbon impact is significantly lower than that of other North American commercial office buildings in the embodied carbon benchmark study. So a thing that was important when applying quite so much hard surface in this main, very tall lobby area was that we had to use quite a lot of sound insulation board behind all of the horizontal and vertical panels to make sure that while this was an open space, it's not a loud space. So now we're out on the north patio in order to show you first how our Katerra CLT panels look in the cantilevered awning, but also to show the Alaskan yellow cedar siding showcased on the north and east elevations. So here we are on the level 2, soon to be occupied deck for the Catalyst building in order to show you the terracotta rain screen system by Schilden that we ordered out of Germany. This system uses a vertical clip and rail system in order to take these approximately 3 feet by 1 foot panels and hold them in place.
All right, will that be it, Sarah, for our tour?
That's all, yeah.
All right, well, thanks to you and all your colleagues that appeared in the videos. We've got, I think, a few questions. Time for a few questions. One question, Sarah, is how is production measured in the CLT plant?
Yeah, the most common unit that we use is meters. And so we have the ability to produce up to 120,000, sorry, is that, oh, my connection is, well, hopefully you can hear me, 20,000 cubic meters of CLT in a year. And to put that in context of building production, building size, you can think about that would give us the ability to produce about 550,000 square foot buildings, so roughly 1 a week, just to give an indication of the potential capacity that we have out of that factory.
Another question that touches on the certification aspects. Does all the wood for the CLT from certified forests, and then they draw the assumption that it's probably not coming from U.S. Forest Service lands?
Yes, so our sourcing strategies are exclusively from sustainable sourcing. We have chain of custody certification with PEFC, FSC, and SFI. Those are opt-in options for clients when they're specifying what they want. And then also our certifications are dependent, I mentioned this morning, on the region from which the timber is coming. So for our SPF product, we're certified on British Columbia South timber, so coming from mostly within 200 to 300 miles of the factory, but southern BC. And then our Doug fir product is certified on Pacific Northwest, so from Idaho, Oregon, and Washington State. But we'll be looking to expand that certification to include U.S. sources on the SPF in the coming year, most likely.
Okay, great. And then just a comment from one of our attendees that kind of references that there are 4 CLT facilities within a fairly close proximity: Northeast Washington, Montana, Southern British Columbia. And they were just pointing out that that certainly, provides a degree of confidence in terms of the volume of wood that it's available, transportation, all the infrastructure, and stable workforce.
Yeah, I think we all feel like we are at the beginning of this explosion for demand for mass timber and wood construction building. And so while there's certainly, and they're just in the last 6 months, 2 new suppliers have come online in the region. So we're, excited about the enthusiasm that other suppliers have for coming into this market. And it's an indication of, where everyone is experiencing an increase in demand for mass timber building. So we're thrilled at the attention that this building product is getting.
Okay, I don't see any new. Here's one. It kind of comes on the heels of the comment on the workforce. So they ask Sarah if you could speak a little more to some of your workforce development initiatives.
Sure. Well, in our Spokane factory, we are, a sizable employer in the local area. I can't, I don't really have any more detail to share as far as how we recruit and develop those staff, but it is a highly skilled. Some of the roles in that factory are highly skilled, given, as you saw in the video, highly mechanized and automated approach that we're taking. And so there's a lot of investment in our team to make sure that the folks that we have are, skilled up and really we're working on world-class machinery up in that plant. And so bringing that skill set to our local workforce in the Spokane Valley is really important to us.
Okay, let me troll for a few questions. Stragglers.
Well, we'd
I
love to
guess-
have folks up for a visit when things are a little bit more normalized. So please feel free to reach out if you're in the Spokane area, and we can get you in. It's impressive when you're in person.
Okay, great. Thanks a lot, Sarah, for being with us for most of the day now.
Thanks,
as
Tim.
part of your panel presentation and the video tours. So I think I'll hand it off. We have our next tour. Han is going to be acting as a little bit of a moderator for that. So I will hand it off to Han.
Great. Great work, all the team members. Thanks, Tim. We have the one more on virtual field trip, which is a very exciting one. Yeah, I am very actually excited about this video presentation because I think the idea is that this technology is going to be able to utilize forest residues to produce the energy products. So we, as a forester, we having hard time to manage the forest residues. I think that this technology may provide a solution to managing the forest residues. So I'd like to introduce the HM3 technology energy company. So HM3 Energy company has been developing its own low-cost torrefaction and densification technology since 2009. With the 2019 Forest Service Wood Innovation Grant they have received, HM3 Energy commissioned on engineering design that estimated plant construction cost for 50,000 tons per year biocoal plant. With this information, HM3 Energy has been able to verify the price for its biocoal will be cheaper than white pellets for Japanese coal replacement markets. And they are thinking that Northern Arizona is targeted as a first location for building a commercial torrefaction plant. So we do have two presenters in taking us to the virtual field trip, working together on this presentation. They are Hiroshi Morihara. He's the inventor and CEO, president of the HM3 torrefaction technology. And we had another presenter, Mary McSwain. She is the HM3 Energy's communication director. So she's been very instrumental in securing numerous grants to help advance HM3 Energy's technology development. Now, what they're gonna do, they have a PowerPoint presentation they're gonna walk through, and then some of the videos are inserted between. They're gonna we're gonna hold our question. We just enter the any question you may have into the Q&A box, and we will address them after their presentation. With that, Mary and Hiroshi, I will let you take it away.
Thank you, Han. Can everyone hear us? Okay, I'm assuming that's a yes. All right, so let me start here. I'm going to have to just say how interesting it has been to watch all the innovation that's taken place in forestry. And HM3 Energy is a startup technology company, but we've been around 10 years and we are at the stage to commercialize what we believe will be an exciting new product for the forest industry. And there we go. Just one second here, I have to get to my right screen. Okay, so just very briefly about us. We have a team of engineers who've worked in multinational companies. They have product process development under their belts, chemical plant construction and operation from the beginning to a startup of a new technology. They have done that. 3 of them have done that already. And woody biomass chemistry and business management. For grants, our very first grant was from the U.S. Endowment for Forestry and Communities for a pilot plant. That was in 2010. And after that, we followed with a number of federal grants, all SBIR, 2 phase 1, 2 phase 2, to advance our technology, for which we're very thankful. Our largest grant, however, was a private industry grant to help with construction of a demo plant to prove the viability of our technology. And the videos that I will show you will be a little bit later as I walk you through what we did at our demo plant and tell you about our technology. And of course, now we're very excited because we're working with the U.S. Forest Service 2019 Wood Innovations Grant. And I will address that mostly at the end of the presentation. So first of all, for the uninitiated, what is torrefaction? Who cares? Basically, torrefying something is heating it, roasting it at a high temperature in the absence of oxygen. And it's been around, the technology has been around for a long time. Coffee beans, when we talk about roasting coffee beans, they are actually torrefying them. Coffee beans are being roasted in the absence of oxygen. So it was a little harder to transfer that technology to using it with biomass. Coffee beans are all similar size, so the roasting is even. When you start roasting biomass, that's a different ticket. So the challenge initially for companies was how to evenly roast, evenly torrefy the biomass. And that even roasting is really critical because you have to have just the right amount of lignin. You can't under roast, you can't over roast. You have to preserve the right amount of lignin to create these briquettes at the end, in our case, briquettes. So as you can see, this is a darker color. It's no longer raw wood, and the properties have changed significantly, which is what makes them a great coal replacement fuel, a carbon neutral coal replacement fuel. Yes.
Mary, may I interrupt a second?
Yes.
Are you showing a PowerPoint presentation?
I am.
We are not seeing anything.
Oh, no.
Can you share the screen?
Okay, I am sharing. Oh, I am not sharing it. I am so sorry. I see now what I did. Okay, I beg your pardon. I will share it. Wait 1 second. My apologies. There you go. Is that better? Okay. I didn't lose them, did I? Okay, so what I was saying is this is a torrefied briquette and this is a Western coal. They're very similar in appearance and they have the same energy content as well. So torrefied briquettes make a great drop-in coal replacement because it has a lot of the traits of coal. It's carbon neutral, but it has virtually no mercury and sulfur emissions, and it has a reduction of nitrous oxide emissions by 50%, which is huge. It can be mixed in any portion with coal, up to 100%. This is critical because if a coal plant is going to start replacing its product with torrefied product, it wants to know that it can start and it can ramp up as that biocoal becomes more available, as more is produced. It has a similar BTU content, energy content, as Western coal. And that's 25 to 30% higher than white pellets. Our product contains no binders. Binders can foul the coal boiler down the road when they're burned. So that's not a good thing. You try to stay away from binders. It can be shipped and stored without cover like coal. And that's going to save on shipping and handling. And it has a similar index grindability as coal. So that means it can be fed to the coal pulverizer, just like coal. It doesn't require a separate feeding system like raw pellets. And in the case of HM3 Energy, this is our feedstock. This is a slash pile from Oregon. It is just, slash piles. The small branches, treetops, bark, needles. We use all that stuff. We're not picky. We take that and we turn it into this biocoal. Okay, I'll go to the next slide if my computer's giving me a little trouble here. Sorry. There we go. Okay, so the first thing we had to do was lower the cost of torrefied product. And we spent 10 years working on this. First of all, we were one of the first to use cheaper forest slash as feedstock. Secondly, we designed our own torrefier that is very energy efficient because, as you can see, it uses gravity. The feedstock comes up at the top and it goes down and it flows using gravity. There are very few moving parts in this piece of equipment. It's a simple and energy efficient design. We don't pelletize our product, obviously. We make briquettes. We use a commercially available densification equipment. It's called a cuber, a cubing machine. It's manufactured by Warren & Berg, a US manufacturer. And torrefied matter is very brittle, and that can create a lot of friction in the dies. So, and that can cause plugging. So we designed a die temperature control system, which you see here. And that way we can keep the dies from getting too hot and stop any plugging. It also ensures that the torrefied material is the right temperature so that when it comes out of the dies, it will make strong, sturdy briquettes. That's an important part of the process as well. So building a demonstration plant was very important during our process development, and we completed construction in 2016. We made numerous test runs using a torrefier and a densifier. They were at commercial scale. The other pieces were commercial in design. And over a 2-year period, we used juniper, we used ponderosa pine residues, we used Doug fir sawmill residue and some agricultural residue. And from these runs, we were able to optimize our technology and gather data on energy usage. And those runs typically, the torrefaction runs typically lasted 24 to 36 hours, nonstop running the equipment. Our longest run concluded at 72 hours nonstop running the equipment linked together. So after working with our equipment and optimizing it, at the end of 2018, we closed the plant and we focused on getting a first commercial plant built using our technology. And here you can see this is our semi-works plant, so-called because the key pieces were commercial size. And this was our original pilot plant. When we got this funding to start construction of a demo plant, we had to kind of shoehorn it in a very small piece of land. So one thing this was zoned light industrial, which meant we couldn't really run it for long periods of time. But the other issue was we didn't have room. We didn't even want to spend the money on an industrial dryer, which you would ordinarily have, because A, that's expensive, and B, it is a tried and true technology. So instead, for our purposes, we put our biomass in containers like this, and we rented heaters and used perforated hose to get our biomass dried. And when we had enough of that stored up, ready for a torrefaction run, we would load it on a conveyor to the plant for processing here. This is our torrefier here at the back end. And I'll be going through these step by step here. The interior of the plant, this is the cubing machine that I talked about earlier. The only size available, even though this was not a commercial plant, was a 50,000 tons per year commercial cuber. So some of the other equipment though was smaller, and so this did restrict the rate at which we could run our torrefier. When we ran our torrefier, we ran it at about 1.5 tons per hour capacity, because the smaller equipment downstream couldn't handle bigger amount of material coming its way. And so here is our commercial size torrefier. It was sized for 25,000 tons per year. This is actually commercial scale. The smallest size commercial plant would be 50,000 metric tons per year output. And so you would have 2 lines with 2 torrefiers. The thermal oxidizer here next to the torrefier was used to destroy the volatile organic compounds that come out from drying the biomass during production. And this unfortunately was undersized, but we made do with it. We were able to work around that somewhat. We have since found a replacement for that. Here's a block flow diagram for a commercial process from forest slash as received from the field to briquettes. We are replacing in our commercial plant the thermal oxidizer with an oxidation catalyst. This is a design by Advanced Torrefaction Systems, and Tom Causer with Advanced Torrefaction Systems is a member of our team and has been extremely helpful in our process development. So this is a great piece of equipment because it destroys virtually all the VOCs. And that's important because when you do have to shut the equipment down for periodic maintenance, you don't want any volatile organic compounds left in the piping whatsoever, because that can turn into tar, and that's not good. The other thing I want to point out is, so the oxidation catalyst burns those VOCs, and then it sends the heat to a heat exchanger, which helps give more heat to the torrefaction process, and it also sends heat to the dryer. So when people say, well, you know, torrefaction, you're heating something at a high temperature, that can't be energy efficient. That's not true. This is what we're doing. We're reusing the energy from burning those VOCs. So that makes our process actually fairly energy efficient. So now I'm going to take you through back to our plant and tell you how we handle that, and I'll show some video clips along the way. So as I told you, I think we only had one of these. This is an expensive piece of equipment. So for our purposes, we just simply divided our process into 2 steps. We made thin pucks in one step, and then we torrefied on another day after we had a bunch of these thin pucks. The reason for making these thin pucks is, remember I told you about coffee being equal in size, and so that's what we needed to do with our biomass. To get an even torrefaction, we had to make our biomass as much even in size as we could. Now, other torrefaction companies have used clean wood chips or even torrefied white pellets to get that size. What we wanted to do using forest waste is we had to change that into something similar in size, and this was our solution to that problem. So we would make a bunch of these and then store them, and then when we had enough of those to run a torrefaction campaign, we would, on another day, we would fire up our torrefier to produce our biocoal briquettes. And so I'll take you through the equipment and that we used for those steps. So step one is the thin puck production. Then we dry the biomass and send it to this hammer mill. And then the cyclone here would pick up the fine particles and recycle, so we didn't lose those. And then the material would be fed through a conveyor to the cubing machine to make those thin pucks. And here's some juniper waste wood. This is the size it was when we received it from the chip truck. The only thing is we did dry it prior to grinding it. So after going through the hammer mill, it's about this size. It's a little bit smaller. And now it's going to come down into this cuber and be produced into raw thin pucks. And we made a lot and put them in super sacks. So after we had a huge number of super sacks full of thin pucks, it was time to heat up the torrefier. And as I mentioned before, the torrefaction runs were 24/7. They were long, at least 24 hours in length, typically 36 and up to 72 hours. So with these thin pucks, then we're going to send them to the top of our torrefier and drop them down through a chute with a slide gate. It's critical to keep the oxygen out of this extremely hot environment, which is over 240 C at least, to torrefy something. So we used a slide gate to do that. And the material would make its way down the torrefier, roasting along the way, evenly roasting as it went down, so that when it got to the exit here, it was at the right torrefied amount, the right roasting time. And it was withdrawn through a screw withdrawal. And now it needs to be cooled before it is exposed to the atmosphere, or else it'll combust. So we have to cool it with a cooling conditioner. We used paddles in this cooling conditioner with some mist spray to convey it to the other end. At the other end, it dropped down through double dump valves here, again, to keep the air out. It's cool at this end, it's hot at that end, so we got to keep the air out still. When it drops out, it looks something like this. It's chocolate brown now because it's been torrefied. And it's now going to be conveyed to a roll mill prior to densification. So here's an overview. And so it's now going to be sent up to be dropped into the roll mill. This is a triple pair roll mill. These are typically used to do things like grind grains and hops and so forth. The material now is no longer fibrous, it's brittle. So this requires very little energy. It grinds quite easily. Dropping into this conveyor here. So now it's gone through the roll mill and it's going to go up this conveyor to the cuber. So it is just come up this conveyor, dropped back into that same cuber, which is now being used to make torrefied briquettes. And it will, we'll probably add a little more water here. There's some paddles in here with spray that we can add more water as necessary to get just the right compaction. And as it'll come out and go through our post densification conditioning oven, this will help set it, give the lignin a little more chance to hold those briquettes and make them a sturdier briquette. And after heating, then they're cooled in this part of the oven prior to storage. So that's our process at the demo plant, the way it was done. So at the end of 2018, we were closing our demo facility and we were trying to find an optimum location for a first commercial plant using our technology. And we got wind of what SWERI was doing and all the ponderosa pine and juniper in northern Arizona. So we took a trip there. And we were fortunate in that trip to, our host introduced us to Dr. Hahn and introduced us to Jay Smith at Coconino County. So we were really convinced after talking with them about how our technology could help provide a market for the forest residue and accelerate the pace and scale of restoration operations. And northern Arizona would be a great place to start. And so we applied for the 2019 Wood Innovations Grant. And I believe Han has already said the purpose of that is to gather key information needed to fund construction and operation of a first commercial 100,000 metric tons per year biocoal plant, production plant. And Erie and Coconino County are our partners on that grant. So just briefly, the requirements for a torrefaction plant site certainly would be a sustainable supply of biomass. And Han's team determined that we didn't want anything longer than a 90-minute haul from the field to the biocoal plant. And it needed to be sustainably available for 20+ years to make the plant pencil out and give a return to the investors. And there are numerous sites that have that. The 100,000 tons per year metric plant would need about 25 acres or more. A lot of that is used for storing the biomass because in the winter months, it's not going to be able to, especially in northern Arizona, you're not going to be able to get in the forest and collect biomass. So you need to store it at your plant, which is running 24/7 all year, except for periodic times when it's down for maintenance. And it has to be 20 years. To produce 100,000 tons per year, you would need roughly 160,000 bone dry tons, metric tons annually. You need access to rail because it's going to be shipped to the coast and out to Japan. Minimal water is needed, but you do need electricity and you need propane for startup. So here you see the rail. It's excellent for shipping out of Long Beach or Stockton. So let's talk about the progress we've made. So far, we're really happy with our progress. The Wood Innovations Grant was really critical. It gave us the funding to commission a preliminary engineering design and construction estimate for a 50,000 tons per year plant. And that's estimated based on Crow Engineering's results at approximately 18.7 million. With this price cost estimate, we were able to do pro formas and estimate a final selling price that is cheaper than white pellets for the Japanese market. I'll talk about that a little bit later. Coconino County helped identify several potential sites with access to biomass feedstock in the 4-5 designated areas for restoration. They also helped us identify some private lands. Each area has the biomass needed. We know that because Han's team at Erie did extensive studies talking about that and showing how much biomass was available. It's very convincing that there's plenty of biomass. And you can download those off Erie's website, those same studies. Erie also helped with logistics and estimated shipping costs from Northern Arizona to those Japanese coal-fired power plants. So with all this in hand, we have now met with and received proposals from owners of 2 potential sites in Northern Arizona to locate a biocoal plant on their properties. And we have also received a letter of interest from a large Japanese trading company to purchase biocoal and to provide funding for plant construction. And we can't thank the 2019 Wood Innovations Grant enough because that really jump-started all this. The company we have been in close contact with actually since May. We're in contact several times a week, and they are very closely following what's happening in Northern Arizona. They're aware of it now, and we're all waiting to see what happens with the contract awards. So here's how we calculated the product cost at the Japanese coal plant burner. So these costs, the burner tip cost for white pellets at $12.53, and for Torah B briquettes, that's our briquette, at $10.34. These include all the costs from biomass collection to shipping, production, and then to the shipping to the coal plant. And it also includes a 20% return on investment to the licensee of the plant. So right at the outset, you notice the energy content of white pellets at 17.5 gigajoules per metric ton versus our content at 22.5 gigajoule per metric ton. There's a vast difference there, and that certainly helps our cause. But let's note exactly how what specific items that is. So biocoal has similar content to coal. So first off, there's no boiler inefficiency penalty. That's this orange section here, where 0 raw pellets are 0.53. That is because white pellets they don't produce the high pressure steam that's necessary to produce the same amount of energy. So there's going to be a bit of a penalty there. Also, biocoal is cheaper to ship and handle if you look at the transportation at 3.83 versus 2.78. It has higher energy density, and it doesn't need to be covered during shipping, so that'll save in shipping costs. And finally, biocoal can be fed to the coal boiler because it is not fibrous. It grinds just like coal. It doesn't need a separate feeding system. And building a separate feeding system to accommodate white wood pellets is extremely expensive. So that adds a lot of cost, this so-called plant modifications, power plant modifications. So that is how we arrived at a comparison to show that we compete and beat white pellets in price. So looking at our business plan, first of all, I want to point out that HM3 Energy, we are a licensing company or technology licensing company. So we talk about building a plant in Arizona, but really what we're talking about is helping someone build a first commercial plant. So we are working very hard to help with the site location, biomass location for a potential licensee, and also funding, and to get that first commercial plant going. With any startup new technology, that very first commercial facility is the hardest to get going. So our short-term business plan is to raise remaining funds and to start construction on a first 50,000 metric tons plant. And then after construction is completed and the plant has started up, hopefully in 2022, then we would begin construction to double the capacity of that plant to 100,000 metric tons. That's why we wanted a site that could produce 100,000 metric tons in the first place. Then at the same time, we would start licensing technology for additional plants. And I am quite sure Northern Arizona has other sites and enough biomass to get additional plants there, but it could be elsewhere as well. And our primary market, the last thing I'll say is our primary market is Japan, and I want to explain why, and probably many of you already know why, but simply Japan will pay much more for coal replacement fuel than our US domestic coal plants. And believe me, we know this because we've tried. And Japan has provided incentives to reduce coal consumption, and they've set policies which will reduce its carbon footprint. So, for example, it has no appetite for nuclear energy, which would have been a solution for them. But after the Fukushima Daiichi nuclear plant disaster in 2011, they lost their appetite for nuclear energy. They have no domestic supply for LNG, so they have to import it, and it's quite expensive. But they do want carbon-free energy sources by 2050, and they want to reduce carbon emissions by 30% by 2030. And to that end, the government has already announced that it is phasing out inefficient coal plants by 2030. Corporations are on notice that they won't be able to run them by 2030. And instead, any remaining coal plants must be high efficiency coal plants. Now, those plants can replace coal with biocoal, but those plants can't even think of using white pellets as coal replacement fuel because they're high efficiency, and white pellets just can't produce the high pressure steam needed for those plants to operate. So that is, we have one more I just wanted to point out. This is our website. On this website, we have a link also to this video, which is a 3-minute video just with an overview of taking the slash and turning it into our biocoal. And Hiroshi is going to answer most of your questions that Han provides us. Thank you.
Great. Well, I think our program will be ended on the 4 o'clock. So me being the moderator role as a moderator, that I want to take a liberty of extending the presentation a little bit longer than what we scheduled, because I think we have many good questions lined up here. So let's take about another 5 minutes to answer those questions. So the first question was, where does Mary, you mentioned about the juniper, where did the juniper came from when you were testing, making some production?
That we are located in Oregon, and that juniper was delivered to us by chip truck from Central Oregon from Restoration Operations.
Okay, Thank you. And then the next question is, can this plant reach the range of 600 degrees plus Celsius to create the biochar?
Well, we've never tried that.
We can.
We could. Yeah. The torrefier can reach that temperature. That's Fahrenheit, right? So yeah, because we were in excess of 500 degrees Fahrenheit in our operations, and so 600 would not be a stretch.
Okay. Next question is, do you have any challenges maintaining the pellet shape in shipping and transporting the final product?
In maintaining what shape?
The shape, basically the durability of the shape of the pellet, the briquette.
The briquette shape. Not so far. We have done 24-hour, our internal criteria was to pass a 24-hour soak test without taking on too much water. So our good briquettes would take on would take on between 10 and 15% water after sitting totally immersed in water for 24 hours. And then we would do a drop test, take it out of the water, pat it dry, and do a drop test from 6 feet onto a concrete floor and measure the pieces that broke off. And we actually did that through a grant with SBIR, and those came out very good. So I guess I imagine in shipping, since we've never shipped a whole bunch of them, we don't have the exact answer to that, but that's been our experience with our own testing.
Okay, great. I think the next question is related to about the conversion efficiency here, about energy content, BTU. So BTUs of biocoal produce, how many BTUs of biocoal can be produced with the 1 BTU input, 1 BTU input of the energy in production?
Our internal analysis shows that our efficiency, thermal efficiency, is about 86%, and that includes the waste of transporting the biomass into the plant, and we use electricity for run motors and all those things. So it's about 86%, but we don't have a third-party evaluation of that.
Okay, great. Hopefully that answered the question. Now, next question is the heat energy for the torrefaction is provided by wood combustion?
Not in this plant, but I can see that happening in the future. We've thought about that, how for the first plant, it's going to be started with propane to start the process. Once the process is going, Hiroshi can address this. You don't need much more fuel because it's so hot and you're burning the VOCs.
Except electricity to run torrefier motors and a few other small motor needs. Otherwise, heat-wise, torrefied material can cover all the heat required.
So I think we have internally discussed how in the future, rather than starting up the process with fossil fuel, using torrefied briquettes, but I think that's a little bit down the road.
Okay, sounds good. Thank you. Next one is, this says that this is awesome. How many employees did this result in?
Well, for the demo plant, you're talking about commercial plant. Yeah, for a commercial plant, it would have roughly 30 operators, maintenance people for each plant. But then you would need, it would be under 30, I think, but you would need about 30 or more biomass collectors and the corresponding jobs of driving the chip trucks. So this would provide quite an economic boon to rural areas, can bring, not to mention the construction of the plant itself, which is great, but yeah, it would provide family wage jobs in a rural area.
So Jeff, you know that this guy, Jeff Holbrook, he says that the great presentation, great virtual tour of the biocoal plant. Next question is, it says that, is this slash transport as ground of feedstock? If so, what type of grinder is needed at the landing? Well, I think that one, I think that belongs to the that question belongs to me. I think that it basically what I've been talking with when I was talking with the Mary and the Hiroshi, basically we can use a traditional standard the type of the grinder can be used to convert the slash into the hog fuel. and then deliver to their plant. And the next question is, would hardwood chips be worth a higher price
As opposed to softwood?
compared to softwood, I guess?
We haven't really tried hardwood,
Yeah,
so I don't know.
yeah.
Okay.
I think hardwood has a different heavy cellulose composition percentage wise. And so we have to do some analysis, and we haven't done that.
Yeah, we focused on softwood for this.
Okay, so I'm gonna quickly, we have 3 more questions. I'm gonna quickly run through, so if you can briefly answer this question. And what is the preferred feedstock for Northern Arizona facility? Sawmill residue, processed slash, small log, or blend?
I think we prefer juniper
Juniper and ponderosa pine.
pine slash.
Yeah,
Okay,
but we've used sawmill residue, so that's no problem.
okay. The next question is, what is the delivered cost forecast dollar per bone dry ton of feedstock for this facility in Northern Arizona?
You want to take that?
Are you talking about?
What
Oh,
we
the
would pay,
feedstock.
what we assume we would pay for feedstock delivered,
Yep, delivered at the plant.
bone dry ton, bone dry ton.
Yeah, roughly we think it'll be about $40 a metric ton by bone dry ton.
Okay, $40 per bone dry metric ton. Thank
Right.
you.
Mhm.
The last question was, how do you guarantee the wood supply when timber sales are litigated by serial litigants? And do you have a backup plan to secure volume, or is this not an issue on federal land in the Southwest? So I think that I can answer that question. I think that in our analysis, we did not incorporate any kind of the risk analysis in our supply analysis. So we learned that we have the sufficient amount of the supply to meet their demand. But with our analysis, did not include that risk, any other risk of fire or litigation or other, the impact analysis. So I think that's I like to say it. And I think it's time's already 4 o'clock. I think that there's a lot of great questions, and I appreciate everybody stay on the session and showing strong interest on this presentation. I'd like to thank you, Mary and Hiroshi. Appreciate it, and that is a very interesting presentation,
Thank you.
and we all enjoyed it. Thank you.
Thank you.
Thanks.
So now I'm now taking this now sending back to you, Damon.
All right, well, thanks everyone for joining us today, and thanks to all the speakers for giving presentations today. That was awesome and really exciting about the future of the forest industry and forest restoration around here. And just have some quick closing notes to end the day on. I wanted to bring all of the team members on the screen that we put together this presentation with. So I'm just promoting a few of them right now. And just a quick note, if you do want CFE credits from SAF and you haven't typed your name into the chat box about that yet, this would be a great time to do that. We'll have the meeting on for another couple minutes. And yeah, I just want to give a big thanks to all the team members that are on the screen right now for helping to put this together. And also Carmen Austin from New Mexico Forestry Division that couldn't join us today. But it's been excellent to work with everybody. And I think we put together a pretty cool day today. So thanks a lot for that. And tomorrow we'll be starting up again at 8 in the morning. And we'll have another round of keynote presentations, and we'll have 2 more panels, one on economic assistance to forest businesses, and the final one on success stories that we've seen in Southwestern forest businesses. So please join us tomorrow for that. And yeah, again, thank you all for joining us today. It's been great.
Thank you, Damon. It's been a great. We appreciate your support and help behind the screen. All right. Okay, everyone, and I'll see you tomorrow morning at 8 o'clock. Again, you can just use the same web link to join back to the our webinar and the same password. So, okay. Good night, and see you tomorrow.